Well, I'm trying to. No, honestly, I got them for charity, so. No, literally, I just you went to the hallway on the outside.
All right, let's go here.
I just picked them up.
Questions on the homework, which was the worksheets,
We didn't really do any
which
homework.
is we did them all except for what, 2 problems? Was that right? We got to 13 or we got to 12 at least, right? It's either 12 or 13 that we got to. There's either 2 or 3 problems left. There's 2. Okay.
Goku card.
All right, hey, Seth, class is started. All right, questions, Danny? Go ahead. All right, I'll collect those here in a little bit. Looking at the calendar, we only have 1 section left, 9.7. I will teach you all of it today. We'll do a quick review about it tomorrow, and then the aforementioned 2 days, although it really should just be 1. Because the 3-day weekend, I don't want to chance it. We'll do 2 review days for chapter 9. You will be so prepared for the chapter 9 test. It isn't even funny. Chandler. Okay, so that's what's on our future. And as the warning I've been making for the last couple of days, chapter 10, every day, absolutely 100%, including the test, you have to have a straight edge and a compass. Now, if you want to use your protractor, that's fine as well, too. Here's your homework for tonight. Copy it down.
Oh, I forgot my stuff.
My original pen.
From August.
Don't worry.
What?
From August.
Yeah.
Okay, can I run your pencils? Yes, can I run your locker?
Hey, your job is to come to class prepared.
Yes.
I already let 2 people go. We're gonna quit right there while we're behind. Make sure you come to class prepared. Sit.
Oh
So.
yeah.
Yeah.
Can I go to Seth's locker?
No one else is leaving.
I'm gonna let them clean myself because I'm about to be then go.
Yes.
Oh, baby, it's coming, bro.
All right, let's slow down. We got some work to do. Not much. The good thing is that it's just, well, it's really one basic idea. However, it's got a whole bunch of flavors to it. 3 flavors. I don't know, chocolate, vanilla, strawberry. So it's one basic idea, but it comes in 2 flavors. 2 flavors. All right. Obviously, the entire chapter deals with circles. This one is going to look exactly like what we've been doing. It has nothing to do with what we've been doing, but the picture looks exactly like we had the last 2 days for homework. It's going to have a circle. It's going to have some chords or some secants or some tangents or combinations of all that. You're going to think that we're going to be doing exactly what we just did. It's different. The previous stuff is all dealt with angle measurements. Each and every time we've been dealing with what's the size of the angle or what's the size of the arc. What we haven't done is what's the side of the chord, secant, tangent. That's what we'll be doing today, is actual finding lengths, not of the arc, but of the parts that make up the angles. All right, that was your note. Remember, you got to have that for next chapter. All right, we've done a lot so far. A quick review of everything we've done so far in the chapter. This is our first theorem, and it says that if you have a tangent to a radius or diameter, then it forms a 90-degree angle. That was 9-1. The corollary to 9-1 says that if you have 2 tangents that intersect, then those 2 tangents are congruent. All right, we've had that before. We'll use that one today, by the way, or tomorrow, sorry. We talked about this arc measure, and that is equal to the central angle. We also had this theorem right here that said if 2 chords are congruent, then the arcs that they make, the ones in red right here, are congruent, and vice versa. If the 2 arcs are congruent in the same circle or congruent circles, then the 2 chords are congruent. Running through these real quick, the next one was the one where you had a diameter or radius, and it is a perpendicular to any chord on the circle, then that radius or diameter bisects both the chord and the arc. Then we had this one, which it's kind of the same idea, but it simply says that if you have 2 congruent or I'm sorry, if you have two chords and they are equal distance from the center, then those two chords are congruent. And it's also vice versa, that if you have two congruent chords and they are equal distance away from the center. All right, so both of those statements. Moving quickly on, now we come to the stuff that we spent, it seems like the most time on, in central, inscribed, and then the angles that are formed outside. Theorem 9.7 talks about the inscribed, it's equal to half of the arc. The one that where you get the x in the middle, that's the one that says that the angle is equal to the sum of the two arcs that it makes, divided by 2. And then last but not least, where we left off, which was this one, where the angle is on the outside, it's equal to the two arcs that it makes, subtracted from each other, big minus small, and then take a half. That's the sum total. I've left off a couple, but that's in general what we've done. The last thing we do in the chapter is this. And this is a crazy amount of information so far. It's a lot of stuff in one little tiny chapter. There is more. We're going to get, it's technically 3, but it's really just one basic concept. This is the one in the entire geometry book that I still don't believe. I mean, to this day, I don't believe this is true. I know it's true because I prove it every year, but for me, I can never wrap my head around why this is true, right? Here's the basic idea. You want to see this? Watch this. You draw a circle, any circle, okay? Doesn't have to have a dot in the middle. You draw one chord, any chord. If I draw another chord and it intersects that first chord, any chord, you get 4 pieces of segments. Do you see them? 1, 2, 3, 4. Can you see those? It turns out when you multiply them together, you get the same number. It's crazy. I can't wrap my head around it. I still don't believe it, but I'll prove it to you here in a second. So it's true.
Oh my
I just can't wrap my head around this thing. Is that when you multiply the numbers together, you get the same values. Now, I'm going to give you a bit more explanation than that, but that's why this one causes me problems, why that picture's right there, because it definitely blows my brain. All right, so here's the general picture. You have 2 chords, and it doesn't matter where they're on the circle. You can have a little tiny one, you can have a big one. Doesn't matter. But if the 2 chords intersect, you see the pieces that it makes? Danny, you're not even paying attention. You see the pieces that it makes? An R, an S, and T, and U? It turns out that if you multiply R times U, I'm sorry, T times U, it's the same thing as R times S, no matter how you draw the picture. You can have a circle with a little tiny one and a huge one. It turns out that that times that is always equal to this. This is why I can't wrap my head around it. That time, and it doesn't matter.
What?
You're like, how would that even work? How's this big honking piece times this little piece equal to that piece times that piece?
It doesn't work.
It does work. I'll prove it to you
Why
right
does that
now.
work?
All right. So this is the first thing. We got to prove this. It turns out that the proof is very elegant and very easy. Anybody want to take a guess at what we're going to make? What kind of construction?
Radii.
It's high school geometry. So what do we always make? We make triangles. So let's make a triangle. I'm going to make 2 triangles. And here's the deal. Here's the big picture. Because of this multiplication right here, this sort of kind of looks like a proportion. There's no division involved here, but I can turn division into multiplication very easy. That's what I'm going to do. I'm going to show that this triangle, the top one, is similar, not congruent, similar to the bottom one. And then I'm going to set a proportion because similar triangles, the sides are in a proportion. So that's what I'm going to do. So we're going to use some stuff that we've already learned before. What do you know about angle A and angle C? What do you know about angle? It's on your paper in front of you too. What do you know about, if you draw the chords, what do you know about angle A and angle C? Why are they congruent? Micah? Go. What do we know about angle A and angle C?
They hit the same arc.
They hit the same arc. Check that out. Look, here's angle A. What arc does it make?
BD.
Makes BD. Look at angle C. What arc does it make? It makes the same arc. Therefore, they have to, by the inscribed angle theorem, they have to be exactly the same value. Okay? So, angle A and angle C are congruent. What about angle D and angle B? The same thing. I get to angle similarity just by using the theorem that we got from this one chapter. Therefore, these two triangles are similar, not congruent, right? They are similar by angle. Therefore, I can set their sides up in a proportion. Remember, this is way back 2 chapters ago. We had similar triangles. And I made a big deal about once you have similar triangles, you just set up a pattern and you follow it. All right, so here's my pattern. Watch this. R times U must equal, therefore, the same pattern on the other triangle. R times U, same pattern on the other triangle, is T times S. We've proven that many times. If you have similar triangles, their sides are in proportion. So that's all I did right here was just call out the fact that since they're similar, then their sides are in a proportion. Hey, do some cross multiplication. What do you get? You get that, which still to this day, I find hard to believe. But we just proved it. We didn't lie about anything. We used everything. And like I said, when I draw the picture like this, I believe it. Can you see that this piece times this piece look exactly like this piece times this piece?
Yeah, I can see that.
But when I draw the circle differently, like this, it's still the same thing.
How?
Agreed. That's why I can't believe this one. If I call this one R, and I call this one S, and I call that little piece right there T, and I call this piece right here U, it's still the same theorem. It's still the same construction.
How would you solve the equation?
Oh, we're going to do it here in a second. But this is why this one causes me from. It turns out that T times U is equal to R times S. All right. The cool thing for us is that even if you don't accept it, although you must now because we proved it, is that the math behind it is pretty easy. So write this one down. Theorem 911. It doesn't say where they intersect. It doesn't say how they intersect. It can be any angle. It doesn't have to be a right angle. It just has to be two chords in a circle that intersect. If you have two chords in a circle and they intersect, then the individual pieces of the chords multiplied together are equal to each other. Crazy. T times U equals R times S or vice versa. It turns out that the math today is pretty simple because all we're going to be doing is doing a little bit of multiplication and a little bit of division. Occasionally we'll be taking a square root. Not often, but occasionally we'll take a square root. This is one flavor where it looks like this. There's two other flavors. 911. When two chords intersect in a circle, the product of one of their segment equals the product of the other chord. That's crazy. And when it says product of a one segment, it means take the two pieces of that one segment, multiply together, saying this product, T times U, is equal to the product of R times S. Good, everybody? Comment? Okay. So it still bothers me that this is true, but it's true. So Ethan said, well, how do we use this? So they're going to give you this construction. One of them's going to be X, and you simply set up an equation. Say it again.
X is just 4.
Well, some people can do the whole darn thing in their head without doing any work, right? I know, you're right. I'm just saying this is a pretty easy thing. I didn't have to prove it to you. If I would have said this is true, you probably wouldn't have believed me. So the setup is this. X times 6 has to equal 3 times 8.
3 times 8 is 24.
3 times 8 is 20, but that's why he already told me the answer. Therefore, X is equal to
4.
Okay, well, that doesn't sound like hard homework at all. It's not. But I know we'll get there to the more challenging ones here in a second. But is everyone okay with what I did right there? Does this look exactly like we just did the last 2 days? You had the X in the middle of the circle. Yeah. Last time, where was the X? It was the angle. So when the X is on the angle, then that's, remember, the two chords added together divided by 2. Now we're solving not for angles or arc measures. We're solving for chord distances or pieces of the chords, their distance. Okay? Anybody lost to what I just showed you? It doesn't get much harder than that. There are two more flavors, but it doesn't get any more harder than that.
So why do we only have 1 through 9?
Say again?
Why do we only have 1 through 9 for
Look at number 8.
All right. Well, we're not to number 8 yet. All right. I said 3 flavors. Here comes flavor number 2. Okay. Does this look like a shape that we've already dealt with? Last night's homework, right? Where the angle is not on or inside, it's outside. Before, once again, we were dealing with the angle and the arcs formed by that. Now we're not talking about the angle or the arcs. We're talking about the segments that are formed. Okay, so when the angle is on the outside, once again, it looks like we get 1, 2, 3, 4 pieces. You see that, Danny? What? You said yes, so what were you saying yes to? What was my question? Do you understand the point I'm trying to make here? Pay attention. This is the easy stuff. Okay. This one has a weirder construction. Do you see it? What's different between this one and the other one? Notice we're getting a distance of the entire segment, right? The entire segment. So R is not this piece, R is the whole piece. T is not this piece, T is the whole piece. Do you see that? It's still the same formula, right? But it's different. I'll go back to this one, right? T is this little piece right here. That's when the angle's on the inside. When the angle's on the outside, T is, or come here, T is the whole darn thing. R is the whole darn thing. So it's different, but I'm still proving literally this is exactly the same thing. Little piece times whole piece equals little piece times whole piece. All right, I got to prove this sucker. Guess what I'm going to do? Guess what I'm going to do? I'm going to make triangles.
I love triangles.
All right. How do we get triangles out of that? I could. Turns out I'm not going to do that. What? There's other ways of making triangles. Instead of going from A to C, I could go
BD.
I could go AD and
BC.
and BC. That's the one I'm going to choose. Okay? Yes?
Why would you make 4 triangles?
You'll see why, because this one works really easy. Watch. Okay. That was construction. What do you think my next step is? By the way, this proof is exactly the same as the other one. What's my next step?
Angle.
What did we do on the previous proof?
Prove if they're similar.
Okay, so let's see if we can prove that those two triangles are similar.
There's 4.
Let's prove that this triangle, ADP, is congruent to CPB. Those two triangles are similar. So how many angles do I need to show that are congruent? 2. Pick 2 angles. Well, just 2. A and B. A and D are on the same triangle. That would be this angle and this angle. There's A and D. I need one from this angle, one from this angle. D and B. So that's this angle right here and this angle right here. Congruent, not congruent. Why are they congruent? It's the same proof. Why are they congruent? Look at the arc that they make. What arc do they make? Look at angle B. What arc does it make? If I go from B and go like that, what arc does it make? Now look at angle D. What arc does it make? It makes the same arc. They're both inscribed. Therefore, what's the relationship between angle B and angle D? They're congruent because they literally make the same arc. Okay? So angle B is congruent to D. We got one angle, give me another one. And even though these are vertical, they're not part of the same triangle. A and C, why are they congruent? They form the same arc. Look, angle A forms arc BD. Angle C forms arc BD. They both form the same angles, or sorry, same arcs. Therefore, they're congruent. It's the same proof as the previous one. Therefore, those two triangles are similar, not congruent. They are similar. Therefore, I can put their sides in a proportion. And I'm going to choose the same type of proportion, just a pattern that's going to wind up with this right here. So my pattern is going to be, watch what I do. You see R? R is on the long side of the top triangle. U, if I pull that one triangle out, here's R, here's U. You see it? So I got R over U, and I got to follow the same pattern on the other triangle. So what's the long side of the other triangle?
R.
R is on this triangle. Look on the other. It's on your paper as well too.
T.
T, and what's the short side of this triangle right here? So T was the long side. What's the short side? It's on your paper. It's box 3.
I don't have the lines on it.
Well, you're supposed to have drawn the lines. What's the short side of the second triangle?
S.
It's S. So it's the same pattern. Long over short equals long over short, both triangles. And from that, it's a pretty quick step into just doing some cross multiplication, and we get that statement. R times S equals T times U. It's the same result as the previous one. It's not the same shape. The previous one had an X in the middle. You're like, well, there's an, yeah, because that's part of the proof. That's not part of the theorem, right? So this is the theorem. So this is the big honking put in your book of truth, right? This is flavor number 2. So this is that construction that's formed with 2 secants. Previous one was just 2 chords. This is the one with 2 secants. So you do have to remember the pattern, though. The pattern is long piece times short piece equals long piece times short piece. This one, I can wrap my head around. This one makes sense to me. Previous one, even though I can prove it every year, I'm like, wow, that just hard to wrap my head around. Notice it literally, the conclusion here says exactly the same as 9/11. R times S equals T times U. But it's a different construction. If you're going to forget one, it's probably going to be this one, because you're going to forget that R is the entire distance of the secant. T is the entire distance of the secant. U and S are the little tiny pieces that are on the outside of the circle. But mathematically, it's just as easy as the previous one. Okay, maybe slightly more challenging. I believe this is Ethan's question. What about this one? It's because we got to have the whole distance. And as soon as we throw a variable, it becomes a little bit ugly, but not too bad. If you're going to get a quadratic, in other words, something to the second power, it'll probably be on this one. But to get rid of squaring, you just simply take a square root. A lot of words. Easy concept. When 2 secants are drawn to a circle from a point outside the circle, the product of one of the secants. When they say product, they're talking about these 2 things multiplied together, T and U. The product of one secant segment and its external segment is equal to the product of the other secant and its external segment. Fancy words for long piece times short piece equals long piece times short piece. You okay? On it? Okay. All right. Last one. I'm not going to prove it. I believe this is a proof tonight for homework. Hey, what's the difference between this one and the previous one? It's got a tangent. So the first one, X in the middle. Second one, 2 secants. This one, secant and a tangent. By the way, this looks exactly like what we had when we were doing arc measures. Okay. Anybody want to take a guess what the formula is?
R times S
Equals,
R times T.
I don't know. All the previous ones we did This times this equals this times this. So what's the problem with this one? There's no other piece. There's only one piece. I still need it to be a product, so what do?
You create.
I don't. There's only one piece.
You use the angle?
So we multiply it by itself.
Oh, what?
So it's going to be R times S equals T times T, which is
2T.
not 2T, T squared. Did you guys like swap brains?
Yeah, maybe.
Okay.
Yeah, I'm letting him borrow it.
Okay.
Today.
You're doing very well today. All right. So that's the formula. This is your third flavor. Neither one of the three flavors are hard to remember, but all three together, sure, it's hard to remember. And this is on top of all that other stuff that dealt with arc measures and angle measures. And the pictures look exactly alike. Hey, it's a circle with an X in it, or it's a circle with an angle on the outside that goes through the circle. Wait, am I doing arc measure? Am I doing angle measure? Am I doing segment measures? This is why we get to test A, you got to be on your toes here. The only cool thing about everything in this one chapter is every single formula is easy. There's no weird or challenging thing of any of this formula. Hey, just multiply two numbers together, multiply some number times itself. When a secant and a tangent are drawn to a circle from a point outside the circle, the product of one secant segment and its external segment is equal to the product of the other tangent's external segment squared. Big fancy words for big piece times little piece equals, I don't know what you want to call that, the tangent squared. Now, once again, this one has a square in it, so we're either going to be solving it quadratically, solving a quadratic equation, or we might be taking the square root. And I believe tonight for homework, most of the ones are all involved just simply taking the square root. I think I signed the quadratic, like, hey, there's something you got to factor, solve it. I think I signed that to the honors, not to you guys. Could be wrong. Could have given you one of them. All right, who's still writing? All right, what do we have left? Just to do some examples, that's it. Hey, if you're going to confuse two of the flavors, it's these two right here, okay? These two right here, because they look pretty similar, right? The difference is that this is a tangent and a secant, and these are two secants. This formula is long piece times short piece equals long piece times short piece. And this one is, it's still long piece times short piece, but it's times this one squared, okay? So all I was trying to do is just point out those two flavors right there. The one with the X in the middle, everybody gets. Now, I will warn you, they can draw some really ugly pictures for you to do this. They have easy ones and they have more challenging ones. So let's do, by the way, these are literally the same formula. You're like, no, this says T squared. Yeah, but it's still the whole thing times the short thing. Right? But the whole thing and the short thing are exactly the same. Okay. So this is an example, box 5, of a very easy one. Danny, can you set it up for me? And this would have been the first theorem we did today. Something done something, agreed. So what are those four somethings? 6 times what? 6 times 8 is equal to? It doesn't matter the order they, because multiplication is commutative. Okay, but I gotta have two things multiplied together. So you said 6 times 8 equals? Perfect. Perfect. All right, let's do a little bit of math. Wes, what's that give me? No. 3x times x is not 3x. It's not 4x. Okay, Wes, back to algebra 1. What is x plus 3x. And what is x times 3x? What's the number in front of x?
1. So it's just,
Numbers with numbers, letters with letters.
so just 3x, right?
Because x times x is x.
X squared.
Uh-huh. So remember, the rule actually says you add the exponents. When you multiply with variables, you add the exponents. 1 plus 1 is 2. So 3x squared. So we have 3x squared equals,
48.
okay? Take a guess what you want to do next. Now, everybody pay attention if you're weak on algebra. Great. We get that. I think everyone can see where that comes from. Now what? We could, but then you're going to take the square root of 3. I'd prefer not to take the square root of 3 or 48. Yeah, we don't have to. We could get rid of the square first. It's easier to get rid of the whole number first, or integer first, the coefficient precisely. So let's divide both sides by 3. That gives me. And by the way, math teachers write these problems. That's why they're nice and pretty, right? In the real world, this wouldn't be pretty because the numbers wouldn't be like 3 and 48. It'd be something else. Now, notice, like I said, the math teacher wrote this problem. What? What? What?
It's 4.
It's 4.
I skipped again.
All right. Well, I know you knew what you were doing, but the doing it was the difficult. Okay. There's going to be a bunch tonight for homework where you have a variable floating around. Sometimes you'll get a quadratic. Like I said, I don't think I gave you any one where you literally have to solve a quadratic using factoring. Most of them will look exactly like this. Can you handle this? We'll do a bunch more of these here in a second. Yes, everybody? All right. This one looks very challenging and ends up being not too big of a challenge if you just declutter the picture first. So cadence, you see a bunch of stuff there. My suggestion is you get rid of something to make your life easier. What do you want to get rid of? It says what? So Cadence says, let's just imagine if that line wasn't right there. Now it turns into that middle flavor, right? Which we can solve pretty easy. Go for it. You might want to look at the theorem so you don't screw it up. So remember, the theorem says it's not this piece times this piece. It's the whole thing times the short piece. And that would give us 9 times 4 is equal to, okay, now it gets a little bit more challenging. And then the quantity, x plus 3. You see what she did right there? Don't panic just because it looks weird, but that's exactly right. Is everybody okay with that? Remember, we ignored, we'll pull the y back here after we solve for x. But let's solve for, or I said, we'll pull the y back here once we solve for x. But let's solve for x first. Okay, what do we do mathematically on this now? Distributive property, that gives us, and that gives us, okay, just a simple algebra problem now. Subtract 9, that gives us, and then divide by 3, so we get 9. So x is 9. So now I can erase the number x, or the variable x, and put the number 9. Now declutter, if you have to, declutter the picture. Sorry, going through puberty. All right, declutter the picture. And now it looks like that last theorem that we just did. All right, Ethan, can you do that one? Now it looks like the last theorem that we just did. No. Look at the theorem. Tell me what it says. Like the math part. Yep.
Oh, all right. So y squared.
So y squared is equal to y times y squared. No. Just use the theorem. What was r though?
9 times 3.
Not 9 times 3. Plus 3.
12
times
2.
2
No, 3.
times 3. All right. So that's what he said right there. We okay with that, Connor? So what's the hardest part of this process? You simply got to remember the procedures. Once you do the procedures, no big deal. But you got to remember that. That's why we write this stuff down in our book of truth. All right, 9 plus 3 times 3. Therefore, y is, good job, Wes, that time. All right, so we went from a picture that looks complicated to start with to a no big deal one, right? That's what the homework will look like tonight. Some of them will be like this, like I don't know what to do first, declutter the picture. Make your life a little bit easier rather than looking at a big complicated picture. Questions? By the way, that's all we're doing today. All right, let's do these real quick together. Connor, was this the first theorem, the second theorem, or the third theorem? This first one on the left. It was the first. Can you do the setup for me?
X times 3.
Okay, so 3 times x is equal to 6 times 4. 6 times 4. Therefore, x equals, boom, look at you. Good job. All right. Wes, first, second, or third theorem?
First, second, first.
It's the first. Okay, a little bit uglier. We can do it though. Tell me what to write.
X, 8 minus x times 4.
What?
Oh, yeah, wait, no, because you,
Keep talking.
3 times x. I know that.
Whoa, whoa, whoa.
Plus, and then you,
Read the theorem.
oh wait, it's time. Yeah, okay. And then it's equals
4 times.
3.
Yes. 3 times 4, 4 times 3. I'm gonna write 12. There you go. Now what?
8x minus x squared.
Oh, it's quadratic equals 12. Ugly. All right. There might be one of these sneaky ones in here. We got to solve that quadratic. All right. I'm going to move these two things to the other side. All right, because I want x squared to be positive. So I would get x squared. If I move that to the other side, it becomes negative, minus 8x. 12 is already over there, so it's plus 12 equals 0. We got a factor. Give me two numbers, multiply 12 to add up to negative 8. What?
2.
Two numbers, multiply positive 12, add up to negative 8. I need two numbers that when you multiply them, you get positive 12.
2 and 6, yeah,
That when you add them, you get to negative 8.
2 and 6. Oh wait, no.
Yes, 2 and 6, except but 2 plus 6 is 8, not negative 8.
Yeah.
So what is it?
It's negative.
Negative 2, negative 6. So this turns into x minus 2, x minus 6 equals 0. 0 product property, set each one equal to 0, solve, we get 2 and 6. All right, 2 and 6. One of them is the answer. One of them may not be the answer. Okay. I don't think there's too many of these floating around, but there might be one. All right. Well, which one is it, 2 or 6? Well, the only way you know is to toss them in. 3 times 4 is 12. So whichever one we plug in for x, we better get 12. Well, let's see what happens if we plug in 2. 8 minus 2 is?
All right, it's negative 6.
8 minus 2 is? Thank you, Cadence. 8 minus 2 is?
Well, 8 minus 6.
Times 2 is?
12.
12. But if we had plugged in a 6, 8 minus 6, oh, it still works. We get absolutely two values that work for it. It's either 2 or 6. We don't know which one. Okay, it's one of the two. All right, who are we on? Matt, last one. First flavor, second flavor, third flavor.
I had to get the third flavor.
Okay, it's no big deal. It's actually, the hardest one is second flavor. All right, third flavor is actually the first and third flavor are the easy ones. All right, tell me what to do. By the way, it's not third flavor. This one is second flavor. Can you see the little piece it's not a tangent.
Oh.
So this one's second flavor. This is the hardest one. But it's no big deal. There's only one variable there. When you get two variables is when you get a quadratic,
I
right?
need to get my glasses. I can't see.
Okay, Velma.
Where's hot dog water? Different.
It's Velma, right?
I call me little girl.
Who's the other one?
Hot dog water.
Hot dog water is my friend.
No, Velma and
Oh, yeah.
Daphne.
Who's that?
Daphne is the
redhead.
is the princess.
Wow, that was actually making me really
Bruh.
That's
Alright.
from Dragon Slayer. Come on.
All right, up here.
It's on Netflix. Watch it.
No, I was doing a Scooby-Doo thing for those.
Yeah, I remember that.
Okay. So what are we gonna write?
X times 8.
Oh, very good. I'm gonna write as 8x.
Okay.
So whole thing times a little piece,
4 times 12.
okay, which is seriously
Yes, seriously.
4 times 12. Well, just do every individual piece here. 4 times 2. 4 times 2.
Oh, wait, no.
He's refusing.
48.
Therefore, x is
48 divided by 8, which is
so. Was this a hard one or an easy one?
easy.
This was absolutely an easy one. All right. 3 more. We'll call it a day. Crit. You want to do 4 on the homework?
Yes, number 4.
All right. Can you draw it real quick?
Oh, I could. It's like.
So you have a circle.
Okay, we got a circle.
It looks like
It's
4 kind of.
Is the angle outside, inside, what?
Outside.
outside.
On the right.
On the right.
So, yeah.
Tangent or 2 secants?
Yeah, it looks like.
Tangent or
Just-
2 secants?
Yeah. Show him.
Number 6. 4.
It's so weird.
So it's the one that Matt just did, right?
But
He just did this one. So we got a 5 and a 3, and a x and a 2x. Okay, so this one's going to be quadratic.
Oh, it's fine. It's fine.
All right, it's going to be quadratic because we got an x and a 2x. So it's still the same. It's the whole thing times a little piece. So the top one is going to give me 8 times 3 is. So we get 24 is equal to. All right, the whole thing is
That's just 3x.
3x times 2x. So I could just write 6x squared, right? This one is actually an easy one. The only time it's the weird one is when you get like a plus or something in there. Okay, but because we could add x and 2x, if this x was like a 3, we'd have problems. Okay, well, you can solve this. How about we get rid of the 6 first? So we got what? Equals. Therefore, x is equal to 2. You know.
Right.
Now it says state the equation would use. Oh no, that's this, not your homework. All right, we still have 3 left. And Chris, you're up. This one right here. First flavor, second flavor, third flavor. First theorem, second theorem, third theorem of today. Second. Okay. Tell me what to write.
Six times x
Whole thing, that'd be 6 plus x.
plus x.
Okay, because it's going to be this plus that. That's the whole thing. So 6 plus x times
5 times 6.
times 6, the short piece, is equal to the same thing on the bottom. Whole thing is,
5 plus 7 times 5.
yeah, so 12 times 5, which is 60. Yeah? Distributive property?
6x plus 36.
And that's equal to 60. Subtract 36 and get 6x is equal to 24. Is that right?
Yeah.
Therefore, x is equal to. That'd be 18. 4. Okay. X equals 4. Very good. All right, Seth. First, second, third flavor.
Number 5.
Yep.
That's the third flavor.
That's a third flavor. Tell me what to write.
6 squared equals 9 times x or 9x.
6 squared is 36. I gave Seth an easy one. X is equal to
44.
what?
4.
4. Okay.
Like that.
Are all these
You
the
said
answers
44. Say again?
Are all the answers 4?
It appears that way. Let's see if we get a 4 for this one. If that's 2, this, well, it could be 4. Let's see. All right, you want to do it? Wes, give it to me.
If this is 4, we don't have to do homework tonight.
8 times,
2, which is 16.
so 16 is equal to, oh, it's 4 again. Look at that.
Oh.
4, 4, 4.
What do you say that?
Illuminati.
Wow. Really, look at it. Dude, I didn't even need my book. I didn't need to pay attention or anything. I already got this down. This is such
I didn't say that today was challenge. I said the challenging part is that the problem is that these pictures look like what we just did with arcs and angles. So on the test, right, I can put the X here on the same picture. I can put the X here. I can put the X here. Now you know how to solve for both. Now I need to put a bit more information to solve for this angle. But if I say this is, I don't know, 200 degrees, right, and the angle is something, you can solve for that. You just have to be careful of whether you're solving for an angle or measures of the secant, tangents, or segments, chords.
Yes. Yes.
All right, that's all I had for you today. Easy peasy. 1 through 9. Who's already done their homework? Okay. 6 was the only hard one.
4 and 8, but 8's just.
Because
Eight is
I hear
fractions,
somebody
I'm
speak
pretty sure I
Spanish,
Yeah,
got it
it's
wrong.
just
I'm just
fraction.
gonna, like, every time I'm just gonna go in the house by myself and
Oh,
get Spanish.
Did
But for me, I have to, like, my entire language settings have to be in
Oh,
Spanish.
I would
I changed them.
Yeah, that's why I didn't.
Yeah, I would. I'm sure they wanted you to do the frac button. Yeah.
Yeah. But I'm just doing it.
All right. Any online learners up right now? The answer to that would be no. All right. Online learners, if you have any questions,
Oh, what do you mean, a lot of you?
that was inappropriate.
They get to sleep. What are you talking